sitting down, so I need to actually. So I need to be closer to here. Yeah, I sit down really.
I sit down.
Who else is talking a lot? Oh, it's better. I might.
Lauren also talks for it.
I'm gonna you guys 2 minutes, 1 minute. 1 minute.
You guys got this.
Live is working.
All right. Well, thank you to my friends and colleagues for being here today. I have the pleasure of introducing one of our students on the Beamline group. This group in particular is from Our Lady of the Rockies in Calgary, Alberta. They've been working really, really hard this whole weekend and even further from that to deliver this presentation. So without further ado, I'm going to hand it over to them and they will introduce themselves and their research. Go ahead.
Great. So sunflowers, see them in a different light or science by Our Lady of the Rockies High School.
The CLS is located in Saskatchewan on Treaty 6 territory in the traditional territories of the Nahiwak, Anishinaabeg, Lakota, Dakota, and Nakota nations, and the traditional homeland of the Métis. The Calgary Catholic School District acknowledges that the land we gather on at Olar Mokinstis is the ancestral territory of the just a bit nervous. Sixikai Sitapi, the Siksika, Gainai, Pekini, and Evskapi Pikuni. We acknowledge all First Nations and Métis of Treaty 7 lands, the Tsuut'ina and the Yithkabay, which includes Bearspaw, Chiniki, and Goodstone.
So again, like I mentioned earlier, we go to Our Lady of the Rockies High School in Calgary, Alberta. We are proud to say it is an institution that promotes the enriching of student minds, which is why we're here for you. So, you're gonna introduce yourself.
We're all in grade 12. I'm Ethan.
I'm Hazel. I'm Danielle.
I'm Stephanie.
I'm Reese.
I'm Lauren.
I'm Tara.
I'm Paul. I'm Elliot.
I don't think that was supposed to happen.
So, time for a little joke. Chemicals in sunflowers. You gotta keep an eye on them. It says that. Thank you. So, the point of our experiment was to answer the question, will sunflowers selectively absorb the cations of calcium nitrate, cobalt-2 nitrate, copper-2 nitrates, zinc nitrate, iron-3 nitrate, and or potassium nitrate into their stems or their leaves? So you may be wondering, why did we choose sunflowers? We did our research and found that sunflowers are best at taking up metal ions into their stems and their leaves and such. They don't require a lot of growing time. They don't require a lot of care or attention. And we are high school students, so we have busy schedules, so it works well with us. And they need to be able to grow in our little closet space in our school we call Narnia. As you can see right over here, there's not a lot of room for too much height, so it worked out perfectly for us. And yeah.
So to begin, we had to make our solutions, and we chose nitrate solutions for their high solubility in water, which allows for the ions to actually be taken up, and it wouldn't interfere with any of our skin. We chose the concentration of 0.1 moles per liter for each ion because we were wary of toxic solutions, and we wanted it not to be too high, but toxicity would pose a problem for us anyway, because a lot of them died. Sorry, guys. We used unit analysis, and the easiest thing we could have done would be our 2-liter containers because we have 2-liter volumetric flasks. And the only solution that was made differently was our ion solution, which came to the concentration of 0.0017 moles per liter after everything was added in to our little big jar, actually. And to grow our plants, we had first needed to sanitize our pots with a bleach solution. Each pot had about 3 seeds initially, but not all of them grew. Before we started watering, though, we had at least 1 sprout for each pot. And they were all grown under a light box, which was on from 5:30 to 10:30. Now, to water our plants, we started watering every 3-ish days. There were like a few exceptions of holidays. Sometimes we couldn't come in, so high schoolers. We started with 40 milliliters per pot, which we found wouldn't make it dry our next water session, but during the winter it got really cold, so we upped that to 50 around December 8th. And we first watered with tap water because we were scared that early germination would leave the plant vulnerable to the sensitivity of ions. And after that, we watered them with their respective solutions.
Some of the challenges we faced were that the flowers ended up not blooming at all. Initially, we wanted to look at the flowers to see if any of the ions we spiked the sunflowers with ended up in the petals or other parts of the flower, but unfortunately, then we never had the opportunity to get those flowers. Another issue we had were that the sunflowers started dying due to the high concentrations of some of our solutions. Cobalt and copper were a couple of the ones that started to die. Those plants started to dry out, so we decided to rehydrate those plants with a beaker over here and a wet paper towel surrounding it. And here is the inside. I'll explain why we did that in a future slide. For our sample collection, we took samples of all our solutions and we put them in this little vial with labels on them. It's the same for the soil, but unfortunately, we did not have enough vials for all our soil samples. So we prioritized our controls, our all ions, and the soils of the sunflowers that died earlier on. For the sunflowers themselves, we took them out and separated those into roots, stems, and leaves, which prepares us for our next slide. We decided to press our samples. So we took a textbook and put some newspaper in between the pages and put all our plant parts in those pages, which is why we decided to rehydrate those dead plants because we didn't want them to be too brittle and break immediately when we press them. We secured the entire textbook with a plastic bag to make sure nothing fell out. And we got advice from our science mentor, Dr. Todd, to do this pressing method instead of freezing them because it'd be easier to transport over here at the CLS.
So you may be asking, why did we choose the ideas Beamline? So all the elements that we chose to water our plants with were all in the transition, like the top part of the transition period. So that's exactly what the ideas Beamline scans for. So we just decided, hey, that's the perfect one for us.
So we used some prototype solution sample holders designed by Dr. David Muir, who was also the Beamline ideas scientist, or ideas Beamline scientist, who helped us with the software and all that. So yeah, for the soil samples, we ground up those samples so we could have a finer consistency and more even, so we could like pack more in without as many anomalies. And we used a dropper for the solution samples and sealed it with Kapton tape. For the leaves, stems, and roots, we decided to do that later. So for the solution and soil samples, we did that on the day of arrival in the lab. But we decided to hold off on the plant stuff just because as they're very dry, they get pretty brittle. So we did that at the Beamline instead. We used a much wider strip of Kapton tape just so we can have them in rows of 3, just so it's more efficient.
So before we look at our data, I'm just going to explain what the XRF is. So we have our samples and we shoot them with the Beamline with a photon light energy straight into the sample. And at the atomic level, we can see the radiation goes in and gives the electron in either the K or the L electron shell enough energy to just kick out. And then the atom takes one from one of the outer shells and moves it in. But for the electron to go to the inner ring, it has to lose some energy. And that comes off in the X-ray lights, which we can see with a detector. And that detector shows us how much energy, and each different element has a different like number of energy, which we can see on here. This side shows how much of the element it binds in it. And then this is the energy. So here we can see, since it's about 3,600, this is calcium. And then it has a lot, as we can tell from here. So some sources of error we could find in our project. So in our all ion solution, we noticed some rusting on the side of the container, which might have messed with some of our concentrations. Also, when we were preparing the solution sample holders, we know some bubbles, which again could have messed with the concentration when scanning. But our biggest problem was cross-contamination, and we were really scared for the newspaper and Kapton tape that we used to prepare our samples. So here we have our tape and newspaper. We scanned them just to see if they had any huge traces of any elements that might like bleed into the plants. So we can see that here, the highest it gets to is like 0.3, but that's like about here on this graph. So there could have been some contamination, but it wasn't that significant.
Okay, so here are our XRF findings that we included with. So we have all of our ion concentrations up here. And using the amazing ideas Beamline, we were able to see the different concentrations that we spiked with within each part of the plant. So if we look at the legend over here, we can see the blue line is our leaf, the orange line is our root, and the green line is our stem. So we managed to scan each of our samples, but we're going to present the ones we found most significant to our research question, starting off with our all-ion sample. So our all-ion sample allowed us to see each of the ions being put up against each other in certain parts of the plant. So as we can see with the blue line leaf, the calcium has a higher peak, meaning that it has a stronger amount compared to, let's say, the potassium, which has a lower peak. Same goes for the root. We can see it has a higher peak in zinc compared to copper 2+. Moving on, our second sample that we deemed most important is our distilled water sample. So our distilled water sample was our control, as when we do water our plants, we normally water them with water. So here we have our distilled water sample. As we can see, in the stem, we found concentrations of potassium to be highest compared to others, and there was a significant amount of zinc compared to other ions, but compared to potassium, it's a lot more lower. So we can assume that potassium has the highest concentration among all of the other ions. And next up, finally, we have our cobalt graph. So cobalt is known for poisoning plants due to its toxicity and reducing biomass. So we decided to present it here to you today. So as we can see, because we spiked it with cobalt, the concentrations of cobalt are a lot higher compared to the other ones, but there is a significant amount of calcium. It does look a lot smaller in comparison to cobalt, but if you look back at our all ions, the amounts are the same. It's just that because we spiked it specifically with cobalt, our scale was blown way out of proportion, and we can see that happen again with our other graphs as well. So here are our observations. Table 1, most evident ion concentrations found in our stems, leaves, and roots and soil, sorry. So these are our samples that we didn't present previously, but these are the peaks that we found most evident throughout all our graphs. So here we have an order ranked from highest to the lowest peaks. So for example, our calcium nitrate, so this would be the plant that we spiked specifically with calcium nitrate. So we can see that the highest peak is calcium, potassium, iron, and bromine, and so on within the stem. Same goes for the other ones with the leaf and then the soil. So the bolded words here are what we found highest in our peaks on the all ions. So we can see that calcium has the highest peak in leaf, zinc has the highest peak in root, and then potassium has the highest peak in the stem. So we bolded these in order to compare what the highest peaks would be like when all the ions are there versus when they're spiked specifically with only that one cation.
So this is a continuation of our first table, and it all makes sense. So zinc has the highest concentration of zinc in their leaves and their stems, but really the only thing that was really odd to us was that in iron, calcium was most present in the leaves. And we think that's because it grew a little bit of mold. And our crossed out boxes are the samples that we didn't bring because, like Lauren said, we didn't have enough vials.
Right, so what we were able to find in our data is that the plants that we chose, they did selectively uptake the calcium in the leaves the most, and then in the roots it was the zinc the most, and then potassium in the stems. Okay, so we did some mapping. I'll explain what that is in just a second. But also with our data, we concluded that if a plant has many options, it will take up everything, but in smaller amounts and less cobalt. So like we had our all ions plant, and it did take up all of the ions that were present in there, just in smaller amounts and a little bit less cobalt. So if a plant only has cobalt, so our plant that was watered with cobalt nitrate, it will take up almost only cobalt and in exponential amounts. So this is our mapping. So what mapping is the beamline. It takes a scan of like a specific point of the leaf, and then we set our scale to like 0.5 millimeters. So basically it scans and then it moves 0.5 millimeters over, and then it takes another scan and it just maps out the whole leaf for the concentrations. So the darker the red, the higher concentration of like each element that we were scanning for. So as you can see in like bromine and cobalt, you have a lot in like the vein here. And then for calcium and chromium, it's a little bit more spread out. And it's also important to note though that we did not actually water with bromine, chromium, nickel, manganese, or titanium. And so in these ones, you can see that copper and iron, little to nothing at all. And then potassium, and all the rest are kind of spread out. And then the zinc has like some in the vein right there.
So, as previously stated, for our research at the beginning of this whole thing, we learned that sunflowers are pretty known for uptaking ions. So, and we saw this with a lot of things, especially cobalt, which is important because with this we can kind of know that sunflowers, they have cobalt. So yeah, so this can be useful because sunflowers are used for something called phytoremediation, which is just cleaning up toxins from the soil using plants rather than expensive industrial equipment and stuff. Another thing this is useful for is sunflower seeds are used for oil that we use to cook and stuff. So obviously the plant can't grow because of cobalt poisoning or some kind of other toxic ion. It's not going to grow effectively and supplies down. Another thing is we should also think about what we're putting in our bodies.
So after we went through with this experiment, we listed some potential improvements to reduce our sources of error or potentially gain some more data. We could have used aluminum foil instead of the newspaper because we were worried that the newspaper might have contaminated our samples, like Ethan said. So that would have taken out that variable. We also could have had more vials to put our soil samples. So we could have compared everything instead of only having a few. And on our part, we could have researched the effects of concentration of certain ions on our sunflowers because, like I said before, some of them died because the concentrations were too high and they couldn't survive. And one more thing is that we could have, if we had more time, we could have had some flowers and more parts of the plants to work with. And finally, we could have grown the plants in better conditions. So maybe not in Narnia where it's a very small space, and maybe not during Calgary winter where it's dry and cold.
So like Ali said before, sunflower oil is used in cooking. So if we could understand what poisons it or what helps it grow, that could help us get more for future research. Maybe there's better plants than sunflowers that we could have used for the uptake of ions. Maybe possibly since the sunflowers are really, really good at growing in different climates and situations. So it would be helpful for the testing of like fertilizer. And since it's really good at picking up cobalt specifically, as we learned, that's found in like sewage from like factories and that stuff. So that can help us clean that out of our earth.
Okay, so we'd like to thank all the amazing people who helped us with this experiment. So Dallas Pelly, who was our coordinator and just answered any questions that we had, was here the time. Mercedes Bai, who helped us in the lab when we were prepping our samples. Tracy Walker, who helped us with our presentation. Thank you very much. Dr. Chris Todd, who was our science mentor, who unfortunately could not be here today, but he was always there when we had a question about like stuff that we needed to do back in Calgary. And then Dr. Rob Blythe, who gave us a tour of this amazing facility.
and Dr. David Muir, who is our Beamline scientist and who showed us how to use the software and the Beamline, which is really cool. And of course, our amazing teachers, Mr. Kozlowski and Miss Saville, who organized the trip and came with us. And we'd also, of course, like to thank the Canadian Light Source for giving us the permission to do our experiment, and to our parents for paying for the trip.
And for the record, Mr. Kozlowski did not steal my minion glasses. He has his own.
Everybody?
This is us happy.
And of course, we got to acknowledge our mascots. We've got Mr. Brown, Bambi, Danny, and Doug.
And now we would like to open the floor up to any questions you may have. We'd like to answer them. Please ask them. Thank you. Yes.
Okay, so in your all ion solution, you noticed some rust forming. Did you notice that also in just the iron?
No.
It was only for the all ions.
Yeah. Hey, that's interesting.
Sure. So you noticed that the plants died because of the high concentration. How might this influence thinking about using these kind of plants for phytomediation? Like, what does it make it better, worse, indifferent?
So the death itself might not have helped, but those results were after it died. So how much it pulled up, it still pulled up a significant amount before it died. So again, maybe future research can show better plants that can like handle it more, but the sunflowers were pretty useful.
Okay, I got one. I have two, actually. I'm gonna say the second one for the end, right, Dallas? I get the last call? Yeah. Okay, the first one though, you mentioned that you were using, for the first time, a prototype sample holder. I also recall that you had some feedback for the designer of the sample holder. I'm wondering if you'd like to share that?
So, one thing that we noticed while we were putting the solutions in is that we were having a bit of trouble getting the air bubbles to escape, which possibly could have skewed our results. So, what I might suggest is that having a slightly bigger, like,
Channel. Yeah.
exhaust port, I guess, and have it more at the end of the slot instead of kind of somewhere just a bit away from the end, so we can tilt it and the air will just go up, I guess.
Yeah, I agree with that feedback.
There's already
Yeah.
a version 2 downstairs.
Other than that, I feel like it worked really well.
Yeah, it was great.
We just had to get a hold, like a hang of it at first. So most of the air bubbles we had were the first ones we tried, because we aren't used to this.
Yeah. With our iron sample, we had a pretty big air bubble in that one, so.
That had a huge air bubble.
Yeah. Thank you for letting us use that, by the way.
Yeah.
It is really cool.
I have a question.
How did you mount in this sample holder the leaves? And then I guess could you walk through like how you mounted the samples?
So for
So I think we just have like a sheet of, like a big strip of tape and then just,
Oh, okay.
Yeah, we
the,
just
kind of
covered,
press them on with some tweezers.
yeah, we just covered that with the tape and
Yeah.
used
And there-
tweezers to put the samples on it gently.
And
so we
there was
break
only
up.
tape on one side of it, so we didn't overlay it with tape after. It was just
Yeah.
one
And
side
to
of it.
add on to that, we did have a problem where one of the leaves curled up.
Yeah.
So then, yeah, we
so
just made
it's
sure.
actually that one leaf that we did mapping on, there's a black spot there that gave us a hot spot that kind of messed up our results a bit.
And
That's
then we
why
did a
we-
new one after.
That's why we did a new leaf of that same type plant.
Which is what we used for the pictures.
Mapping.
Yeah.
Yeah, but then for the sample folder that David made, was it different? Was it the soil samples then?
The solution and the soil sample.
No, we didn't do
We
the-
didn't use this as
You can see that the ones here with the channels, these are the solution holders
Oh, for
and
the
the other
solution,
ones are the soil.
Yeah, sure. Very cool.
So this is the standard one that we typically work with.
Yeah.
And then this one is a prototype of the channels.
Got you there. So for filling in that type. Very cool. And it was, Dallas, correct me if I'm wrong, you allowed 2.5 hours for sample prep.
I
And using
know.
the fresh, it's something done in 45 minutes.
Yeah.
Wow. So it cut down a lot of time. Yeah, very cool.
Okay, are you ready for mine now?
Oh, Patty had a question
Oh,
too.
okay,
It's
sorry.
just a little question. I noticed that you had your lights on, for 18 hours. Why 18 hours?
So it was really cold and it was starting to be winter time. So we were really worried about if this were to affect our results, if it would grow at all or grow better with more light. And it got really dark really fast. So we were kind of just like worried about it. We set it to more time than we needed.
So did you have, grow lights? Or you
Yes.
just
Yeah.
regular lights? A thing that you could have done because of your heat, is you could have put down a heat mat.
That would have helped a lot. If we were rich. If we were rich.
We were.
Where were you 4 months ago?
At my desk.
Patty has some plants in her office, her resident plant.
I don't have any right now.
Yeah. I have a question. So you're all grade 12s. I'm wondering, you talked about future research in regards to sunflowers, but if hypothetically you were invited back and you were to do some research of something that you're interested in, now that you know what XRF is, now that you know what mapping is, anybody want to just take a shot at what they might be interested in doing in the future? What's the future research?
Well, there was the research about the fish eyes. I found that really that was really cool. I feel like something to do with that.
Maybe like animals.
Yeah.
Or like, I remember Dr. Rob, like when he did the tour, the story about the amniotic fluid inside the lungs.
yeah.
That's like way down the line, like maybe
Yeah.
20 years when more experience, but something along those lines where it directly affects like healthcare in that sense. That'd be
Or like
Yeah.
how certain like minerals and stuff affect like our hair and nails and like other stuff. Like there's already a lot of research into that, and maybe we could take that maybe a step further with all this equipment.
I agree with what Danielle said, like learning more about like how things work for medicinal reasons could be really useful.
Okay, I've got two things. I'm going to shift away from the science learning that you've done and ask you a question that is more about your experience going through this process. You've been working at this for quite a long time. You've had a few challenges that you've had to overcome, and you've done a really, really good job. I hope you're proud of yourselves, because I'm certainly proud of you, and I hope you feel that too. I would like each of you to answer this question, if at all possible, and that includes your teachers. What of this experience do you feel like you're going to take with you as you finish out high school and maybe go on to post-secondary and kind of go forward? So what has really stood out to you that you have learned that you'll carry with you?
Yeah, I'll start. Definitely teamwork. Like working with this huge of a group and splitting things up and putting trust in other people. Like, I know you're gonna get that done, and I trust that you'll do it. That was a really valuable experience.
I feel like the organization of everybody, we kind of picked up roles really quickly, and I feel that was
like moving on from that, but like teamwork, yes, but also like the whole aspect of researching, especially because I don't know, a lot of us applied to like a STEM program, and it's like in high school we don't really get exposure to that, so it's like jumping in head first into something we don't even know about. So this experience allowed us to kind of see what we have in store for the future, which is really nice. So now I feel more comfortable, at least with going into university, applying to the STEM program.
Yeah. So for me, I really enjoy doing this research. So I think I might pursue like a research career in the future. So yeah.
I think for me, it's probably the the practice of asking questions. Because I know like when we got our data, it wasn't just like, okay, this is what it says, I'm accepting it. We were always trying to find out why this, why that. So I think anything I do, I'm probably gonna carry that practice of, okay, but why, you know? Yeah.
I think for me, it's like knowing where to put yourself and what to do and when to just let other people handle it themselves. Because you can't do everything. We have a lot of things to do, so we gotta split everything up. And I think it's just trying to trust other people to get things done.
For me, I saw a lot of like in the science community, everyone's like really trying to help each other in different fields of stuff, and it's kind of interesting. Like there's a bunch of different people, there's like physicists and a bunch of other people that specialize in different things here. And I find that like really nice that there's like this big collaboration of everyone with completely different interests.
Yeah, I agree with what was said before about teamwork though, because we became really efficient when we knew what we were doing and we were all working together, like in the lab. And also the value of like asking questions. I feel like I learned a lot from asking rather than just waiting for the answers.
Teamwork? Yeah. Teamwork? Yeah. Teamwork. Okay.
Makes the dream work.
It reminded me to trust the process because we will get there in the end, but there's going to be all sorts of ups and downs, and that's okay. Along with that, I relearned that, and I have to remind myself all the time of this, deadlines are still good because they help me, and I know most people that I'm work with kind of get to the end and get something done because without a deadline. So I just need to do this first and that for ends. Things just kind of happen. And so having some deadlines are definitely.
Yeah, I loved learning how to use all the stuff and watching all of you guys learn too and learn with you. The hardest part for me, I think, was not like directing you so much, like letting you just take it on. I had to like stop myself a few times and just walk through. Like and like not that I trusted you to get there, but like sometimes we like to help a bit more, especially at school because our classes are only so many minutes. So we by the end of the class we need you to have mastered this concept. Whereas here we had more time, so I had to train myself to just step back, keep my mouth shut.
Any last comments?
Thank you all for coming and watching our presentation.
Thank you.
Thank you.
All right, thank you.
All right, on behalf of the CLS team, I just want to say thank you to the team. Thank you to my colleagues and everyone for attending and supporting the students. There are some chocolates in the back and some coffee if you need some. But with that, we're going to do a little bit of a closing with the stuff later, but we're all excused. So thank you. All right.
Thank you.